Welcome to NPTEL online course on fractals and multifractals. So, in the last class we have discussed the multifractality, how it differ from the fractal measures like Hausdorff measures and Hausdorff dimension, how it differ from the Hausdorff dimension and fractal dimension. And we discussed the moments of the Cantor set and Dyadic Sierpinski triangle. Then there is a conservative quantity in the Sierpinski triangle in the Cantor set. Surprisingly, that conservative quantity is the moment value. That moment value is not an integer, it is the fractional value. Then we need to discuss the multifractality of the Sierpinski triangle as well as the Cantor set. As we defined fractal in two manner, one is the random fractal as a regular fractal. The random fractal in the sense it has the self similarity in the statistical manner. The regular fractal in the sense it has the self similarity in the exact manner. So, while constructing the iterated function system also, there are two type of construction. One we usually constructed by using the Banach fixed point theorem, other one we introduce the condensation set. So, thereby we add the external force and we affect the exact self similarity, we are getting some partially self similarity sets. Then we discussed their dimensions. Now, here in the moment, through this moment, we showed that there is a conservative moment for the Cantor set as well as in general in the fractals. Now, we add some random flavor in the Cantor set and the Sierpinski triangle. Then we will discuss the fractal dimension of the original one and the added flavor in the multifractality, that means we added some random flavor in the self similarity. So, now we will have, there are two type of Cantor set. One which is the exact self similarity, another one is the random self similarity Cantor set. Then thereby we can discuss the fractal dimension for both the set and multifractality for both the set. Then we will compare the multifractality and fractal dimension for these two sets. So, for that first we will discuss some random fractals, then thereby we will discuss the multifractality and fractal theory. So, for that we will try to construct Dyadic Cantor set. Dyadic Cantor set, we are taking unit interval, dividing the unit interval into 3 equal parts and removing the mid open interval. This process is continuing an infinite number of time and take the intersection of all the process, then we are getting the Cantor set. This we are calling the Dyadic Cantor set. Now we will discuss the Dyadic Cantor set with some probability flavor which help us to include the random self similarity. So, here the Dyadic Cantor set TCS start with an initiator which is typically an interval, closed interval 0, 1. We are start with the closed interval 0, 1. The generator then divide into 2 equal parts. We are dividing this one as 2 equal parts, whereas in the Dyadic Cantor set we divide 3 equal parts and removing the mid open. So, the generator then divide into 2 equal parts and delete one. Say the right half, we can delete any one, we can delete write one with the probability 1 minus p, with the probability 1 minus p. So after the step 1, the system will have on average 1 plus p number of subinterval of size 1 by 2. Here after the first step we have this 1 by 2 and we may have this one or we may not have this one, depends on the probability. So therefore the after step 1 the system will have an average. If this one is here, then we have 2 interval, otherwise not a 2 intervals. So on average totally 3, so we will get 1.5. Therefore 1 plus, if you are taking the probability as 1 by 2, we will get that 1.5 interval 3 by 2 will get. So the system will have an 1 plus p number of subinterval, each of its size is 1 by 2. Each of its size is 1 by 2. Since the right, this is the left hand, this is right hand, the right hand interval remains there in the step 1 with the probability p. This is confirmed. This is after first step, the right hand will remain same with the probability p, the right hand with the probability p, and the left hand side with the probability 1 minus p. Say that we give a piece of thread and scissor to n number of people, thread and piece to the n number of people, to divide the thread into 2 equal parts. Divide the thread into 2 equal parts. We then give them a fair coin and ask them to remove one of the 2 pieces. If the outcome of the toss of the coin is head, and keep both the pieces if the outcome is tail. We can give them a fair coin and ask them to remove one pieces of, we will give the thread to n number of people and ask them to cut in 2 parts, toss the coin. If we are getting the head, they need to remove 1 pieces. If the tail, they need to keep these pieces. This would correspond to p equal to 1 by 2. And hence in the limit n tends to infinity, half of the people will have 2 intervals and the half of the will have only 1 interval, to make the average number of interval equal to 1 plus p, where p equal to 1 by 2 in this case. The same rule we are applying here, which n tends to infinity, half of the people will have 2 interval, half of the people have 1 interval. So take the average of this one, then we will get 1 plus p. The same rule, if p equal to 1 by 2, we will get 1 plus p. The same rule we are applying here. Now in the next step, the generator is applied to each of the available 1 plus p subinterval to divide them into 2 equal parts. Again we have 1 plus p subinterval, divide that one as 2 equal parts. In average we have 1 plus p interval. The first rule is applied in the second set again, that means generated after the second set, the 1 plus p interval. Cut into 2 pieces, remove the left side with some probability and right side with some probability. Then divide it into equal parts and remove that right half from each of the 1 plus interval with probability 1 minus p. So we are to delete one, say that, oh sorry, we are removing the right half, this is the left half. Fine. Remove the right half from each of the 1 plus interval with the probability 1 minus p. The size 1 by 4 will then have the average 1 plus p square. 1 plus p, and we will get one more 1 plus p, then 1 plus p square. Number of interval of size 1 by 4 as 1 minus 4 time 1 plus p number of interval of size 1 by 4 are removed on the average. This number of interval removed on the average. then the same process, the process is then continued onwards, and so the same will be generated on the available interval at each step recursively. Like its definition, finding the fractal dimension of dyadic Cantor set problem is also a simple. Now the resultant after infinite iteration will take the intersection, will finally will get the dyadic Cantor set. Now we need to find the dimension of the dyadic Cantor set by using usual method. So according to the construction of the DCS, there are n 1 plus p power n interval in the nth step, each of which have the 2 power minus n. So 1 plus p power n interval, number of interval, and each of its size is delta is 2 power minus n, and hence it is also the mean interval size. The mean interval size is this one. Now like in the recursive triadic Cantor set, we can construct the nth moment md of the interval size at the nth step of construction process of TCS 2 and find that here too it is a conserved quantity. That means n of delta we can take as delta power minus df. The number of delta needed to cover this is 1 plus p power n, and delta is 2 power minus n. If you are applying here, then 1 plus p power n one can write as 2 power minus n, though one get 1 n df. So the df we can get ln of 1 plus p power n by 2 power n, ln of 2 power n, then one get ln of 1 plus p over n times ln of 2. This n will cancel, then ln of 1 plus p over ln of 2, right. So once again, the most convenient yardstick to measure the size of the set is the nth step. The mean interval size is 2 power minus n, which coincide with the individual size of the interval in the nth step. So expressing n in favor of the delta, that means this power relation, we can find the df. Df value is ln of 1 plus p by ln 2. The probability is lies between here and here, 0 to 1. Therefore this ln of 1 plus p is less than 2. Therefore this quantity df quantity is also less than 1. So this dyadic Cantor set, if we are finding the df fractal dimension is ln of 1 plus p by ln 2. So here one can observe that the fractal dimension of the dyadic Cantor set depends on the probability p. If probability approaches to 1, if this probability is approaches to 1, we can increase the dimension, the numerator will get increased to 2, then finally the df value will increase to approaches to 1. The df value, if p approaches to 1, then the df value is approaches to 1, because the numerator ln of 1 plus p will approaches to 2. By decreasing the p value to 0, then if you are decreasing this p value to 0, then df value will approaches to 0. So it means that by adjusting the probability, the density of this dyadic Cantor state we can adjust. That means how the usually the fractal dimension provide that how the object is dense in the given set, how much space it is occupied in the embedded space. So by adjusting the probability, one can find the different dyadic Cantor set. Now note that the exponent df is non-integer, at the same time it is less than the dimension of the space 1 because it is embedded in closed interval 0 comma 1, dimension of the space 1. Where the set is embedded, if we have 0 less than p less than 1, it is the fractal dimension on the resulting dyadic Cantor set. Unlike triadic Cantor set, where the Cantor dust are distributed in the strictly self-similar fashion, the Cantor dust is in the dyadic Cantor set are distributed in the random fashion. Yet it is the self-similar, but it is the statistical sense. In the Cantor set, we are dividing into 3 equal parts and dividing the mid open in all the process. Therefore, the dusts are equally distributed. The Cantor dusts are distributed uniformly it has the same self similarity, that means strict self similarity. Whereas in the dyadic Cantor set, the Cantor dust, that means the points are distributed randomly based on the probability. By adjusting the probability, we can take into 2 or we can take into 1 of its dimension, and the distribution also random distribution. With respect to the probability, the distribution is random. So it also exhibits the self similarity, but in the random sense, in the statistical sense. So this one, the triadic Cantor set, is example for the regular fractal or deterministic fractal, whereas the dyadic Cantor set is example for the random fractal, because the self similarity in the random sense or statistical sense. Now in the triadic Cantor set, we calculated how much interval we removed from the closed interval 0 comma 1 and obtained the Cantor set. Then the resultant we got as 1, because in the each iteration we are removing 1 interval of 1 by 3. In the second iteration we are removing 2 interval of length 1 by 9, and the next interval 2 power 2 interval of length 1 by 3 power 3, and goes on. If we take 1 by 3, we will get this series. This series represents the length of the removed intervals, that means sum of the length of the removed interval from the closed interval 0 comma 1, which is equal to 1. That means we are start with the closed interval 0 comma 1, then this sum gives the length of the interval we removed from the closed interval 0 comma 1 and obtained the Cantor set, which is equal to 1. Both are 1. It means that literally there is nothing in the Cantor set, but we already discussed some enough result in the Cantor set. It has the infinite number of points, and fractal dimension also lies between 0 and 1. Now this leads us to conclude that size of the set that remain is precisely 0, since the sum of that are removed equal to the size of the initiator. The question is, does that dyadic Cantor set 2 possess the same property? Whereas similar to the triadic Cantor set, we constructed the dyadic Cantor set by including the probability. Now the question is, the dyadic Cantor set also possess the same property. For instance, on the average in step 1, the amount of size removed is 1 minus p by 2. In step 2, the total amount of size removed is 1 minus p times 1 plus p by 2 power 2. In step 3, 1 minus p time 1 minus p power 2 over 2 power 3. If you are going the next step, in the fourth step, 1 minus p time 1 plus p power 3 by 2 power 4 will get. So it goes and so on. Now we need to find their sum. So sum is, that means 1 minus p by 2 in the first step, then 1 minus p times 1 plus p by 2 power 2 after second step. The second step, in the third step, 1 minus p time 1 plus p power 2 over 2 power 3. In the fourth step we will get 1 minus p times 1 plus p power 3 by 2 power 4 and goes on. If you are taking a 1 minus p by 2 as common, then we will get 1 plus p by 2 plus here 1 plus p by 2 power 2 plus 1 plus p by 2 power 3 and goes on. We will get this series will get. So, this series we can write as like this one. This is 1 minus p by 2 summation n equal to 0 to infinity 1 plus p by 2 power n. Now, you can observe this quantity 1 plus p by 2. This quantity, the p is lies between 0 and 1, the probability value. It is lies between 0 and 1. So, this value is less than 1. This value is less than 1. Therefore, it looked like the geometric series n equal to 0 to infinity r power n 1 plus r power 2 plus etc. So, it converges to 1 over 1 minus r. When this r is less than 1, this value is less than 1. So, apply here. So, you will get 1 minus p times 2 times 1 over 1 minus p, this is 1 minus p, 1 plus p by 2. So, 1 minus p by 2 times 1 over 2 minus 1 minus p over 2, then you will get 2. So, one can get 1 minus p over this 2 will cancel. Here 1 minus p or 2 minus 1, 1 minus p which is equal to 1. So, this sum, what is this sum? This sum stands for the, which is again the size of the initiator. It means there is hardly anything left in the set, nothing. However, we will show later that there is a still tons of member in the Dyadic Cantor set. So, one of these virtues of the Dyadic Cantor set is it is simplicity. This example classified the notion of random fractal and its inherent character with self-similar nature. Fine. Now, what is the comparison between the Dyadic Cantor set with the Dyadic Cantor set? Here, we are constructed the Dyadic Cantor set with the initiator 0, 1. At each step, divide every available interval into 2 equal parts. Keep the left half, always we can keep this left half. Previously, I explained this as R, but the left half we can keep it, and the right half with the probability p, delete it with probability 1 minus p. So, after the first step, keep the right half with probability p, delete the left half with the probability 1 minus p. So, this p may present, this will present, this may present, we are not deleting. So, we will get 2 intervals, delete with the probability this one as 1 by p, again we will do in the same procedure on the step 1. Now, we an average we will get 1 plus p number of interval. On average, we will get 1 plus p interval size 1 by 2 because split it into 2 times. In the second step, you can split into 2, therefore, it will get 1 by 4, 1 by 2. We can split 2 with the probability, again this side is p, this side is p. Similarly, p minus 1, p and p minus 1 and p minus 1, if you multiply, then on average 1 plus p power 2 interval of size 1 by 4. So, after nth step, on average we will get 1 plus p power n interval of size delta equal to 2 power minus n. if for example, which I already explained, p equal to 1 by 2, give n people a thread and scissor, each cut into 2 parts, toss a pair coin, head means remove the right half, this remove it, tail means keep the both the halves. Half the people keep 2 pieces, half the people keep only 1 pieces on average. So, average number of interval is 1 plus p, that means p equal to 3 by 2. The same rule we are applying here. Now, for finding the fractal dimension, so in the nth generation it has number of pieces is, average number of pieces is 1 plus p power n into their size is 2 power minus n. So, apply the power law property, then we will get the probability this one. Here the df value is lies between 0 and 1. We are starting with the closed interval 0, 1. Therefore, this set is the fractal in 1D. If you are finding the total removed interval, it is equal to 1. We obtain now the total interval 1 by using this geometric series property, because this if r is 1, this geometric series consists to 1 minus r. Now, our 1 plus p by 2 is less than 1, it is because the p is lies between 0 and 1, this quantity is less than 1, therefore, this series converges to 1. Now, in the summary, for each interval we have one initiator, we have the one interval of size, expected number of interval is 1, the diagram is like this one. In the interval size is 1 by 2 in the first, after first interval, then the 1 plus p number of interval, that figure is here, and 1 by 4 is the interval size, 1 plus p square is here, it is here. So, left half means it is blue, right half keep with the probability p, right half removed with the probability 1 minus p is given here. Now, the comparison between the Dyadic Cantor set and triadic Cantor set, that means the deterministic fractal and random fractal, this may be the scaling, it will differ again and again, it will has to go. Maybe this is after n step, this comes like this one and goes on. Now, here the distribution is random manner, the distribution is here in the deterministic manner. Here the fractal dimension is the fixed number ln 2 by ln 3, here the fractal dimension is ln 1 plus p by ln 2. So, this is the example of random fractal which has the self similarity in the statistical sense. If you are taking p equal to 1 by 2, then the fractal dimension of the Dyadic Cantor set is 0.5, even less than the fractal dimension of triadic Cantor set. So, now one can understand that by varying this probability p between 0 and 1, we can give the dimension in 0, 1. In between 0, 1. We can give the 1-to-1 correspondence between the number in 0, 1 to the Cantor set which having the fractal dimension df. We can give the 1-to-1 correspondence. Suppose if we are taking p equal to 0, right half is always we removing. Right half is we are always removing. If p equal to 0 means ln 1 by ln 2, ln 1 if p equal to 0, then we will get ln 1 is 0, the fractal dimension will get 0. That means we are always keeping the right inverse. There will be nothing in the Cantor set. It is a single point left at the end. Only one point will end. If p equal to 1, right half is always we are keeping the right half. That means we are cutting 2 parts and keeping the right half always. So, we have then it is just we are dividing and joining, dividing and joining, dividing and joining. So, it is the whole interval. Ultimately, if you are taking the union, you will get the whole interval. In that get the fractal dimension is 1. So, the fractal dimension 0 is possible, fractal dimension 1 also possible, because in the end we will get one single point 0, and here will the whole interval 0, 1. If you are choosing the probability between 0 and 1, if you are choosing the probability value, here if the probability value is 0 to 1, one can get the fractal dimension lies between 0, 1. We can give the 1 to 1 correspondence. So, here it shows that how the number of interval grows with respect to the 1 by delta is here the 1 to 1 correspondence we can give. Now, this is the comparison between the random fractal and how it differ from the deterministic fractal, the fine example. Now, we need to apply the multifractal formalism on this dyadic Cantor set as well as the triadic Cantor set, because the multifractal formalism not only for the random fractals. We can apply the multifractal, it is a measure, this measure we can apply on all the sets. We will check if apply this multifractal measure on the random fractal, what is the effect. If apply the multifractal measure on the deterministic fractal, then what is the effect we will discuss. So, in the dyadic Cantor set, df the moment of the interval size at any stage is during the construction process is equal to 1. It means we can consider each interval as a cell containing a mass equal to df the power of the size of the interval. Now, in the triadic, the formalism is if the cell are labeled I equal to 1, 2, 3 etc. in the each iteration, then we can find the measure mu I as xi power df, mu I equal to xi power df. The xi is the size of the interval on each step. Then corresponding partition function is defined here, is that q is mu I power q by taking the sum of the defining the moment of the measure mu I. This is for the discrete case we are taking the sum. In the continuous case we need to take the integral 0 to infinity mu I power q c of x comma d into dx. Now, let us discuss the dyadic Cantor set. So, in the nth step of the construction there are 1 plus p power n number of interval, each of its size is xi equal to 2 power minus n, and hence the mean measure size is also delta equal to 2 power n. Now, before that, before applying the multifractal formula, this one, in the dyadic Cantor set we have 2 power n interval, each of its size is 1 by 3 power n. So, this also obeys the power law property with respect to the size of the interval and the number of interval required to cover or in the each interval. So, we obtain df equal to ln 2 by ln 3. That means 2 power n is directional proportional to the 3 power n df. We obtained this ln 2 by ln 3. So, in the each xi, as we already defined, the xi is each of its size is, that means the length of the interval is 1 by 3 power n. For I equal to 1 to n, the n equal to 2 power n. So, if you are applying the partition function here, then the number of interval times 2 power minus n q df. That means delta equal to minus 1 minus q df, so that the tau key is 1 minus q df. Applying the Legendre transform is f of alpha equal to df. That means if you are applying f of alpha, we are getting ln 2 by ln 3. Ln 2 by ln 3. So, it says that the multifractal spectrum, if you are drawing here with respect to the alpha and f of alpha, the alpha also will get single value, the exponent also single value, will get the single exponent, not even straight line, we will get the single exponent. Now, just to modify the construction of the dyadic Cantor set, here the support is the DCS with the fractal dimension df ln 1 plus p by ln 2, on which the total mass of the initiator will be distributed heterogeneously. However, before we do that, let us first apply the multifractal formalism to the TCS and show that it is resultant is a unique F value instead of the F of all of spectrum, like a triadic Cantor set. Recall at step 1 the generator divide the initiator of unit R into 2 equal pieces and remove one with the probability 1 minus p. In the next, the generator is applied to each of the remaining intervals to divide them into 2 equal pieces. If we continue the process, then in the nth step we will have 1 plus p power n interval of size 2 power minus n. That means delta equal to 2 power minus n. And we already know that in large delta limit, n limit, the resulting system emerges a fractal with respect to this property, the different fractal we can get. Now, however, here we want to apply the multifractal formalism so that we can appreciate the difference between the fractal and multifractals. In order to apply the fractal formalism, we must have to know what to choose a measure and find what fraction of this measure is in the ith cell. These two things is important. What to choose a measure and what fraction of this measure is in the ith cell. We begin the simpler case where the generator divides the initiator into 2 equal parts but removes the right half with the probability 1 minus p. After the step 1, there are 1 plus interval of size 1 by 2. In case of, we assume that each cell is occupied with the constant equal to 1 by 2 power df. In step 2, we divide the interval of in the left side into equal parts and remove the right half with the probability 1 minus p. Similarly, the interval which is there with the probability p is also divided in the same fashion. Then at the end of step 2, we shall have 1 plus p power interval of size 1 by 2 power 2. If we now continue this process, we will get 1 plus p power n to interval size 2 power minus n. We conclude we could describe the occupation probability of each ith cell pi as xi power df. Now we will find this summation. I equal to 1 to 1 plus p power n, pi equal to 1, because we have 1 plus p power n interval, their size is 1 by 2 power n. If you take this summation, it 1 is the independent of the step n, because we are, as we comes from the triadic Cantor set. If you are taking the dfth moment, then one can get this as 2 power minus n df, and this is 1 plus p power n. Now we know that 1 plus p power n is directional proportional to 2 power n df. So if you apply here, then 2 power minus n df times 2 power n df, one can get as 1, like the triadic Cantor set. If you have a deep moment, it is 1. This df also the conservative quantity in the triadic Cantor set, because it is the independent of the step number n. Now the so called partition function psi q is defined as I equal to 1 to 1 plus p power n pi power q. Now pi we are defined as xi power df. This is the different. Now here we are finding the dfth moment, mdf moment, which is equal to 1. This df value we are raising the power of each of its sizes. xi is the size of the interval in each of the interval has the size, this one, that means 1 by 2 power n. Now raising the power this one as df, that we are making as the probability, because if you are taking this total probabilities as 1, now the measure pi is defined like this one, pi equal to xi power df. Now will partition function xi q is defined like this one, pi power q, that means mu I power q. We are defining the partition function for I equal to 1 to n, which is given in the procedure of multifractal formalism. We are taking the mu I equal to xi and the df, that conservative quantity, because if you are applying each interval as a cell containing a mass equal to df, dfth power, it will equal to the initiator in total size of the interval or the size of the initiator. We are constructing recursively. Now this is the important thing. Now we are creating the probability as xi power df. Now taking the summation of this one power q. So now instead of simply covering the sets, we are considering their density, what means their size, or there can call it as a mu is the measure of the each of the sub interval. If you are taking the sum of all the interval, it equal to 1. The total mass 1 we are getting equal to the total mass. Now eliminating in favor of s, that means the delta, then we are taking here the delta as s. S equal to 2 power n, we can get that xi q is, because we know that the partition function is delta power minus 1 minus q df, will get that means s df, we get this z q is delta power minus tau q, delta power minus tau q. Therefore, we will get the tau q as 1 minus q df. Now the df value we are obtained as ln of 1 plus p by ln 2. We know that the mass exponent should satisfying the basic condition. If you are substituting q as 0, it must give the dimension of the, that means the fractal dimension it must give. If you are taking q as 0, if here the q as 0, not p, the q as 0, then one can get df ln 3 by ln 2. And if you are substituting q as 1, we can get 0, this much satisfied. It is worthwhile to mention as a passing note that Hastil and Procoria introduce another set of dimension by defining tau q as 1 minus q dq. With respect to the q, we can find the dq. This result are available in this paper written by the Procoria and et al. That the infinite number of generalized dimension of fractals and the strange attractor, physica d, the nonlinear dynamics. This paper, this results they introduced. That this dq we can call it as the generalized fractal dimensions. Generalized fractal dimension. By varying this q, we can get the different dimension. Now take the Legendre transform of this tau q, then we will get the f of alpha. Before that, here a system can be described as multifractal if dq depends on the q. In such cases, d naught is just the dimension of the support, that means a fractal dimension. d1 gives the information dimension and d2 gives the correlation dimension. Therefore, we are calling dq, that means the generalized fractal dimensions or generalized dimensions in the plural form. So now taking the Legendre transform of tau q, one can get f of alpha equal to 1 plus p by 2. Thus, instead of getting f of alpha as a spectrum, we get a constant value and hence it is not a multifractal. Since the slope of the mass exponent is the same regardless the value of the q. The tau q value is same regardless the value of the q. The mass exponent value is the same regardless of the value of the q. Because we are raising the power q, mu I power q, that means we are taking probability q as xi power df. So, if you are raising the regardless the value of this q, the mass exponent is same, the slope of the mass exponent is same. So, we are getting the single point. Also in the f of alpha, this does not depends on the alpha, this does not depends on the alpha. So, you can think about, we will get, see, we are taking the interval, and dividing two equal parts, whether we are removing this left half with the probability 1 minus p, with the right half with the probability p. Then again we are applying here and here, there is no change in their density, this distribution is no change. If we are keeping this one also, like this one we are getting, again we are dividing 2, then we are keeping this one or this one or this one or this one, there is no change in their density. So, as mentioned in the definition of multifractal, if you have the smooth curve like this one, if you divide the equal parts, if the curve or smooth curve, if you are fixed the delta, the each box has the same measure, the measure of the box is same if you are choosing any delta. If the curve is like this one, suppose your curve is like this one, some zigzag curve, if you are taking different delta, if you are divide this one as like this one, here with respect to this delta, box measure is different, the measure of this box is different, this box is different, so that we will get different alpha. For the different alpha, we will get the different f of alpha. But here in the uniform case, we are not getting the different alpha. The mass exponent is the same regardless the value of the q. If you are raising any q, we are getting the same. So, here though it is a random fractal, the f of alpha spectrum we can get as a constant, value, and hence it's not a multifractal, since the slope of the mass exponent is same as the value of the q. It is not the multifractal because we are getting the spectrum as a single dot. So, we conclude with the note that the resulting system is fractal, since the fraction of the total measure contain the same in each of cells of the same size. So, in that case, the fractal dimension is enough to classify how the object is dense in the embedded space. There are two things now we discussed. One is triadic Cantor set, another one is random Cantor set. In the triadic Cantor set, the self similarity is deterministic manner, the exact manner. In the random fractal, the self similarity is not exact manner, the random manner, because based on the probability here, based on the probability whether we are keeping right hand side or removing the right hand side, it depends on the probability. Whereas in both the comparison, if you are compare, their distribution is uniform. How the points are distributed in the interval, it is uniform. There is no change in the how the density of the boxes. Each small boxes are, if you are covering this one, by some collection of sets, this one by some collection of sets, then each collection, if you are taking any interval and by changing the boxes size, there is no variance in the density. Here also then same thing following. So that then the multifractal spectrum, the alpha exponent, we are not getting the different alpha exponent, we are getting the only one single alpha exponent, the corresponding to the f of alpha is a single point, it is ln 1 plus p by ln 2. So though it is a random fractal, if you are finding the multifractal spectrum, we are getting as a single point. Then notable thing. Now then if we are changing the self similarity, it does not create the multifractal spectrum. The self similarity alone does not change the multifractality. Also inside the each iteration or in the self similar properties, how the points are distributed, that's matter. In both the set, points are distributed equally. Now we need to give some example such a way that the system should have random self similarity and the points are distributed ununiformly, then we will find the multifractal spectrum. Then we can compare with the triadic Cantor set and other multifractal set in the next class. Thank you. So here the reference are given, Dense-Speeder and Falconer, the more detail available in the Dense-Speeder as well as the Falconer with the probability theory. Thank you.